So the last section in chapter is optimization. Basically, it's the word problems. We've been doing these problems over and over again, finding answers, but we haven't put them in the form of a word problem. So optimization problems are problems that involve finding the absolute max or min of functions. If you find the absolute max or min, that could be maximum profit, maximum revenue, or you can minimize cost, or minimize area or maximize area. Common optimization problems involve finding area and perimeter, maximizing revenue and profit, and inventory control. So the first one we're going to do is example 1, area and perimeter. What are the dimensions of a rectangle with area 225 square meters that has the least perimeter? Okay. So if L and Y represent the length and width of the rectangle respectively, we know that the area is L times W, length times width, is 225. And we know that if it's a rectangle, the perimeter is 2 times L plus 2 times W. So we start with two equations. And we can solve for one variable and plug into the other. And we end up with a perimeter function. So let me walk you through this point here. Okay, so on our piece of paper, we know that area equals length times width. That we know. So we know that the area, length times width, is 225. So there's our first equation. Is everybody comfortable that if I tell you if it's a rectangle, and I tell you the area, you know that length times width is 225. Is everyone comfortable with that? Okay, basically if we have a rectangle, length times width, you can figure that part out. So there's equation 1. And if it's a rectangle, we know that the perimeter would be 2 times L, there's 2 L's, plus 2 times W. The perimeter, which is 2 L's plus 2 W's. Does everyone see how we got those two equations? Are we okay? And the problem said, what dimensions, length and width, of the rectangle to have the least perimeter? So anytime I ask you for the max or the min or the most or the least, that's an optimization problem. And when you think optimization problem, you should think extrema. And you know how to do extrema. Take the first derivative, set equals 0, see if there's anything defined, see if there's any endpoints, check all that. That will give you your extrema. Okay? So are we trying to find the minimum of the area or of the perimeter? Perimeter. So that's the focus, is the perimeter. But the problem with the perimeter is we have two variables, L and W. I don't know how to solve for two variables. So what we first do is we use the area problem. And let's say we solve for L. So divide by W, we get L equals 225 over W. Now, first of all, why am I doing that? Why am I doing that? Because I can't deal with the perimeter function right now because it has two variables. But if I take what's given, use that, plug it into the perimeter function, where there's an L, I put 225 over W. Now, am I dealing with one variable or two variables? Only one variable. That's really the trick to this first example. I'm trying to minimize perimeter, but I have two variables. How do I deal with those two variables? use the given, and plug it into the one I want. Are we okay? Now, this is where it becomes a regular problem. Perimeter equals, and I'll even give you a head start, 450 w to the negative 1 plus 2w. Okay, I've given you that because you know if I ask for extrema, what do you have to do?
Take the derivative.
Take the derivative, set it equal to 0, and solve. See if there's any number that makes the derivative undefined. See if there's any endpoints. There aren't any endpoints. I'll talk about this. We can come up with some, but I wouldn't be concerned with the endpoints. Okay? But I'll give you a couple minutes because, again, the problem you have is algebra. Algebra, algebra, algebra. Let's give you some algebra time. And remember that proportion trick we used on the last one. Yeah, for another minute, because again, the issues we're having are algebra issues. Okay, so if you take the first derivative, you get negative 450, w negative 2 plus 2. Did we take the derivative correctly? Okay, now that gives me negative 450 over w squared plus 2 equals 0. This is algebra, 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 and it's the same algebra I've already covered. It's the same algebra we've covered in the last problem. I'm going to add 450 over w squared, add 450 over w squared. 2 equals 450 over w squared. What have I just created? A proportion. Solve the proportion. And again, it's the same trick as last time. So are we copying it down, or are we actually understanding it? Are we copying it down, or are we actually understanding it? Now finish. What? Add, cross multiply.
Oh, you do it like that. Okay.
When you cross multiply, you get 2w squared equals 450.
Yeah, I just
Divide by 2, divide by 2. Again, there's other algebra ways to do it.
instead of bringing
W squared equals 225. Square root, W equals plus or minus what? 15. Now again, this is what's nice about a word problem, and it kind of ties to endpoints. Can you have a length of negative 15? So it doesn't make any sense. We know that one of our restrictions is it has to be positive, so we only get W of 15. What's nice about word problems is they kind of bring a reality to things. Even though I got two answers algebraically, the only answer that makes sense is positive 15. But if you can't do that algebra, this is our second example today, plus you've had algebra. Okay? Got to get your algebra skills up. Now, the second thing we look for extrema is we look at the derivative. Is there any number that would make that undefined? And the answer is 0. But again, let's talk about reality. Can you really have a width of 0? No. Now, as far as endpoints, we can kind of say it has to be greater than 0 because it's a length and width, and it can't be at most something that would make the area more than 225. So I could play around with it to figure out the endpoints, but in reality, if I'm trying to minimize or maximize something, the extremes won't work. The extremes won't work, right? If I did 0 to 225, we don't want one side that's really high. So after all this work, what did we find the width to be? So if I find the width after this work to be 15, is this in feet? This is meters. There's your answer. Now your job is to find length and to find perimeter. So we did the work to find the 15, like the work we've been doing. Now your job is to find the length, and once you have the width and length, you can find the perimeter. Okay, so if I have the width, what will I use to find the length?
the original.
Which original?
Area.
Yep, L times W is 225. If I know that L times W is 15, divide by 15, divide by 15, what do we get for L? 15. Are we okay? Then, how do I figure out perimeter? 2 times L, L is 15, plus 2 times W, W is 15. What do we find for the perimeter? 60 what? Okay, take a minute. Any questions? Yep.
Not to be like super technical.
Yep.
But did you say it was a rectangle or a square?
Squares can be rectangles.
Yeah.
Not all rectangles are squares.
Yeah.
Good question. We okay? Now, I am going to add a bonus, right? I think it's nice to know, but you may be wondering, how did I know if 15 meters was an absolute max or an absolute min, because we were trying to minimize perimeter. How am I supposed to know? Well, remember, the original was 450 W to the -1 plus 2W, right? Was that the original? If I want to check if something is absolute min or an absolute max, you take the second derivative. So the first derivative is -50 W -2 plus 2. What would the second derivative be?
900 W.
900 W to the
-3.
-3. And what number? This would be 900 over W to the third. That's the second derivative. What number are we going to plug in? What did we find for W? 15. And if you take 900 divided by 15 raised to the third, you get 0.0267. That is greater than 1. And when you plug into the second derivative, sorry, less than 1. When you plug into the second derivative, and your value make sure I did that right, is less than 1. Oh, 900, I'm sorry. That's wrong. 900 divided by 15 raised. Which good? 0.26? That's less than 1. And when it's less than 1, you have an absolute max. It's the opposite. Okay? So plugging into the second derivative lets you know if you have an absolute max or an absolute min. Oh, sorry, 0. I'm sorry. That's the problem. Sorry about that. So you take the output one more time. When you do this, you get 0.27. Since that result is greater than 0, you have an absolute minimum. If your result is greater than 0, you have an absolute minimum. And what were we trying to do to the perimeter? Maximize or minimize it?
Minimize.
Minimize it. So this is how you verify. Again, this is bonus. I think this is bonus. To verify if the 15 is an absolute max or an absolute min, you take the 15, plug into the second derivative. If the result is greater than 0, you have an absolute minimum. If the result is less than 0, you have an absolute max. And again, I think this is nice to know. The real work is right here. The real work is right here. Okay? Word problem number 1. Let me go through real quick how they worked it out. So we had our perimeter. We found the first derivative, set equal to 0. When we did that, we got the numbers -15, 15, and 0. But the only number that worked was 15. If I plug 15 into the second derivative, it's greater than 0, which means we have a local minimum. The least perimeter is W, 15. You plug into the area to find that width is 15, length is 15, plug into the perimeter, and we got our answer. Okay? Second example, example 2. Again, these are the ones dealing with area. A homeowner has $320 to spend on building a fence around a rectangular garden. As shown in the drawing, 3 sides of the fence will be constructed with a wire fence at $2 per linear foot. The fourth side will be constructed with wood fencing at a cost of $6 per linear foot. Okay? So if we look at the picture, we have 4 walls. These 3 are fence. $2 a foot. This last wall is wood, which is $6 a foot. Okay? And we have $320 to spend total. Find the dimensions of the area of the largest garden that can be enclosed with $320. Okay? So, first of all, we have two things going on. We have area going on, and we have money going on. Okay? So let's break this down and get our two equations. Once we have our two equations, then we can work on solving. Okay? So, step one. We have a rectangle, and we know the rectangle is x times y. So, what would be the area of this rectangle? X times y. There's equation one. Questions on how we did that? Now, taking this a little step further, if this is y, this is y, if this is x, this is x. We okay? This one's $2 a foot. This one is $2, this one's $2. But this last side is what? $6. So how much money do I have to spend total? $320. So if I take 2y plus 2x plus 2y plus 6x, that has to all equal how much money? $320. So 2y plus 2y, 2x plus 6x gives us 8x plus 4y equals 320. The very first thing we need to do is talk about what's given. And there's our first two equations. Stop there a second. Does everyone see how I got two equations? Okay. And then let's clearly write down the goal. The goal is to maximize area. Maximize is your clue that we're going to do extrema. And the one we're going to do the extrema on is area. We okay? Stop there. There's your setup. Any questions? Now, can I maximize area right now when I have two variables? Nope. So I use the other equation, and I solve for one of the variables. Let's solve for y. Minus 8x, 4y equals negative 8x plus 320. Divide by 4, y equals negative 2x plus 8. So just like last time, we use the given, solve for a variable, and now we're going to take that y and plug in for area. So area will be x times negative 2x plus 80. So area equals x times y. Instead of y, I put in the negative 2x plus 80. Area equals negative 2x squared plus 80x. That is what I'm going to try to maximize. So if you think about this one and the last one, that's what they both have in common. You have to start with two equations. You're trying to minimize or maximize one of them. Use the other one to plug in, so you're only dealing with one variable. Okay? Now, because of time, let's do this together. Okay? So we're trying to maximize, so we do extrema. What's the thing we do first? Take the derivative, negative 2x plus 80, set it equal to 0. Take the derivative, set it equal to 0, solve. Subtract 80, Negative 4x equals negative 80, divided by negative 4, divided by negative 4, x equals 20. Okay? So far, we have one answer of 20 feet. Does that answer make sense? Is it possible to be 20 feet? Yep. And again, because we're doing extrema, we want to just double check our three things. The second thing is looking at the derivative. Is there any place this could be undefined or dividing by x or anything like that? None. And then the third thing are endpoints. They didn't give us any endpoints. We can kind of figure out that, it has to make sure that it equals 320, but the extremes would not work. So I don't have to worry about endpoints. So bottom line, we found x. So once we find x, which is 20 feet, your job is to find y, and your job is to find the area. So once we find that one piece, that critical piece, then you can find y, then you can find area. Okay, so how would I find the y? Which one would I have to plug it into? Go back to the original, 8x plus 4y equals 320. I know that x is 20. 8 times 20 is 160. Subtract 160, subtract 160. 4y equals 160, divide by 4, divide by 4, y equals 40. So x is 20 feet, y is 40 feet. How do you find area? 20 feet times 40 feet gives you 800 feet squared. That would be my maximum area. That would be my maximum area. Okay? And that's half of 4.5, 4.6.